Hello everyone, welcome back to my channel. In our ongoing series of neural networks from scratch, we have been discussing about different loss functions. To be precise, we are discussing about regression loss functions. So we have seen mean squared error, mean absolute error and different variants of mean squared and mean absolute errors. And also we saw smooth L1 loss and Huber loss, which are one of the most used for regression tasks. And today we will discuss about log functions. So how we can use the logarithmic function as a loss function. Usually logarithmic functions we might have seen in classification tasks as cross entropy or categorical cross entropy losses like that. But how can we use log function for regression? That is what we will see today. And before doing that, we need to understand some properties of log functions. Why log function is used in regression? For understanding that, we need to understand the properties of log. These are the commonly used log functions. So log to the base e, which you can say it as natural logarithm, which we usually say it as ln, log to the base 2, log to the base 10. So these are the commonly used log functions. Now let us observe the graph and understand what are the different values of log for different values of input. Okay, so let us see that we have x here, okay, on the x-axis, and we have log x on the y-axis. Now I want to understand for different values of x, what will be the log value. So from the graph itself we can understand from minus infinity to 0. So this is going like this, right? The curves are going like this. So log is actually undefined. We cannot calculate log for negative values. At the same time, we cannot calculate log for 0. Log exists for positive values. And then from 0 to 1, this is actually negative values. Whatever is there in between, these are all negative values till 1. At 1, it becomes 0. Okay. From minus infinity to 0, it is undefined. And from 0 to just before 1, it is all negative values. And at 1, it becomes 0. And after that, till infinity, these are all some positive values. Okay. And it becomes 1 in between somewhere. Okay. Where it becomes 1, we will see from the graph. So these are the common values of log. If you see this graph, so these are all undefined below 0. And from 0 to 1, you can see this is the area. From 0 to 1, all these are negative values, right? All the graphs are negative. So that is what we have seen here. And after that, from 1, these are all positive curves. What about this 1? What is the significance of 1? So log will become 1 when x is equal to its base. Okay. If you see this here, this is becoming 1 at 2. What does it mean? This means here x is 2 and base also 2. So that is why it becomes 1. And this natural logarithm becomes 1 at this point. This is almost like 2.7 something, which is the value of e, right? So if x becomes e, this becomes 1. And base 10, log to the base 10, it becomes 1 at 10. Because here it becomes log 10 to the base 10, which is 1. So this is becoming 1 when x is actually equal to its base. And beyond that, all these are positive values. So we know that all these are positive values, but what is the trend going on here? As the values are increasing further, the curves are getting flattened out, right? So the curves are getting flattened. So that means that a large difference in x, okay? So x is large difference is there, but then your log of x, it's almost the same. Very small difference, right? So this is one property we want to see. Now we want to understand how this property is useful in case of regression. So in case of regression tasks, where do we see large values of x? Usually in outliers, right? So large variations in x indicates that our data has outliers. So in case of outliers, when there is a lot of difference, we can use logarithmic error, okay, which will kind of balance out the error. Now, if we use other errors like mean squared error or absolute error, so the errors are proportionate to the outliers. If there is an outlier, so the error will be very high. And for MSE, it is even higher because it squares the term. Usually, your learning algorithm is biased towards the outliers. So the error is kind of making the algorithm misleading, saying that it is making a lot of error, but usually it is contributed by a single value or two values. So this is one area where we can use logarithmic error. usually the data distributions, we assume that these are following the normal distribution. That is the assumption. In case of regressions, whatever the data you are using, it should follow the normal distribution. But there is a skewness in the dataset. So in real world dataset, you cannot guarantee the normal distribution. So there can be skewness. So what exactly is skewness? Skewness is actually the data which is not symmetrically distributed around its mean. So if the data is not symmetrically distributed around its mean, that means that there is a skewness. If you see this normal distribution, this is the mean value and the data is properly distributed here. Whereas if you see these things, the data is not properly distributed and the same thing here, it is not properly distributed. So this is what we call it as skewness. So there is a positive skewness, there is a negative skewness depending on whether it is biased towards the left side or biased towards the right side. It is having more weightage towards the right side or more weightage towards the left side. Depending on that, we can say it is a positive or negative skewed data. So now for regression task, it is bit difficult to fit this kind of data sets, the skewed data set. So for handling these kind of skewed data set, we can use logarithm values. So one beautiful property of logarithm is it can convert these skewed data set into normal data set, means normal distribution. So whatever the skewed distribution is there, it can actually convert into normal distribution. Why? Because of that flattening curve. So that the characteristics of logarithm, if it is this kind of non-transformed data, that means that this is your original data set and it is clearly skewed, you can actually convert that into kind of normal distribution by applying a log function on top of it. This is one more beautiful property. This is actually, we call it as symmetrizing the distributions. So it is making the distribution symmetrical. So it is symmetrizing the distribution. So whatever the non-symmetric distribution is there, it is making it into symmetric by applying the log function. This is one more beautiful property of logarithm. Now we will see at a higher level what are the advantages. So one advantage is it will actually symmetrize the distribution, right? So it makes the distribution symmetric, whatever the non-symmetric distribution is there, where you have the data is spread across very widely and it is not in the normal distribution. You can actually use logarithm to convert into symmetric distribution. And also we have seen this, the effect of outliers. Usually outliers will induce the error. And if this error is very high, your weight updates will go haywire. So usually the weight updates depends on your error. So that is where you calculate the derivative, right? So you take the derivative of error with respect to the weight values to get then update value. So if your error is very high, your weight updates has to modify a lot to reduce that error. But usually because of outliers, the total error is contributed by hardly few outlier samples. So there it is kind of the training, the whole training or learning of regression is kind of going misleading. That is where if you use logarithm error, for large values also, it is kind of having very small value. So that's why your error becomes smaller even for large outliers. So it is not misleading in this case. And also linearizing the relationship. This is kind of, if your distribution is kind of exponential, like you are having e power x or some other power exponential relationships, then it is a bit difficult to actually do the regression tasks, especially linear regression or even some polynomial to up to some degree. It is a bit difficult to actually fit this kind of distributions when you have exponential variants. So to reduce that to linear, you can actually apply log. You know that e power x and log of x is opposite to each other, right? So this is one more benefit. So now because of all these benefits, we can use this logarithmic term in our error function. So if you use this in our error function, then it becomes like this. So let us understand one by one. Okay. So the first thing is logarithmic error. That means that you apply log value to the actual and the predicted value. So you apply log to actual and predicted. That is what we are doing here. So this is the actual value, let's say, and this is my predicted value. We are applying logarithm for both of them before even taking the subtraction. Okay, this is the error. So actual minus predicted, that is the error, right? So error is actually actual minus predicted or predicted minus actual. You are anyway taking the square, so it doesn't matter. So this is the actual term and this is the predicted term. and you are taking the logarithm of them before even subtraction. What about 1 here? What is the significance of 1 at both of these places? We saw that log of 0 is undefined. So when you have this actual value or even predicted value, let's suppose that if they are becoming 0, then what about log? It is not defined, right? So to avoid that, we add 1. So the total logarithm, even if it is 0, it will not be undefined. So now the log of this one, so this is only for the computational benefit. Okay, so you are taking the log of them and then you are subtracting them. That is what logarithmic error is, right? And then you are taking the square of them, square of this difference, similar to MSE. So you are taking the square of them. And then you have n samples, okay? So your dataset total has 100 examples or 100 samples. All of them, you take this difference and then you take the average. So this is what summation and then division by number of. So that is what it is mean. So totally it is taking the mean of squared logarithmic error across the whole data set. So that is what we are doing. So you can see this is y is actual and y hat is predicted value. Log x, usually we take the base. So that means the natural logarithm ln, which we usually denoted by ln. So this is what we take it here, log. So this is the mean square logarithmic error. Now because of this log function to your predicted value or actual value, your total error, even for the outlier values, the error will be very small. Even for large values also, the error values, when you take the logarithm of it, automatically it becomes smaller, right? That is one of the property here, useful property. Now let's come to the derivative. We all know that yes, it is a square term, definitely derivative should exist, okay? Because the property should be derivable. Every loss function should be derivable to use it in gradient descent or any kind of learning algorithm. So here it should be derivable. So it is kind of like x square here. So usually derivative of x square is 2x. So I can actually ignore this term and then this term I can make it as 2x. So 2 times this total term, log of 1 plus y, okay, minus log of 1 plus y hat. So this is the 2x term. And after that, in place of x, we have this total term. So we need to take the derivative of that. So we need to take derivative of log of 1 plus y minus log of 1 plus y hat. Okay. So let's keep this term as it is. Now we need to expand this inside. So when I do that, I will get, so this term will come here same. And this term dou by dou y of log of 1 plus y minus dou by dou y of log of 1 plus y cap. So what happens when you take the log of this one, derivative of log? So derivative of log of x, if you have, derivative is 1 by x. So that means that this becomes 1 by 1 plus y minus this becomes 1 by 1 plus y hat. Okay. And this total term here 2 times log of 1 plus y minus log of 1 plus y hat. So this is the total derivative here. So you can even further compute this one, modify the expression and then further compute till you reach a final expression. So it doesn't matter, you can actually continue. So the derivative exists here for this one. That is the main point. Now let us see the advantages of using this error function. Okay, logarithmic loss or logarithmic error. The first thing is it handles large range of values. So automatically it seems like it can handle outliers. So this is a valid point. We already have explained this. And it has a balanced error representation. This is one point I was saying. So usually if you take mean squared error or mean absolute error, all these things, because of outliers, let's say you have 100 samples of data and you have 5 outliers. Okay. So out of your 100 samples, 100 samples, you have five outliers. Now the error value usually, because of these 5 outliers, it will be very high. Okay, MSE will be very high because of these 5 outliers. Okay, so because of which the error is kind of misleading. So what happens now, if you want to do the weight updation in the regression task, okay, in your neural network, usually if your error is very high, then your weight updations will be, it's not fine, it's coarse update, right? So just because of these 5 values, all the other 95 are doing good. Only because of these 5, it is doing coarse update. So that is what, it is not having a balanced representation of your original error. Okay, whatever error you are getting, it's not an actual interpretation of how many samples are doing good and how many samples are doing bad, right? So that way, when you use logarithmic loss, even for these outliers, the error value is smaller, right? We have seen that. So overall, you will have a balanced error representation. So you will understand that, okay, by seeing the error value, you will understand that how good is your predictions, right? So that is one. And we have seen this point already. It is robustness to skewed dataset. So when you don't have a proper normal distribution, when you have skewed distribution, either it is positive or negative, usually it is a bit difficult to apply the regression problem. But when you use the logarithmic loss, it kinds of takes care of that. So it is robust to this kind of skewness. We'll see this point. It actually penalizes small errors compared to large errors. So that means that when you have outliers, okay, the error should be high. That is what the MSE or MAE will give. But usually because of this logarithmic term, even for large errors, the output will be smaller. And for small errors also, the output is almost in the similar range. That means that we are penalizing the small errors more. Let us see in detail here. You can see this here, right? So the actual prediction is 40. The actual value is 40 and predicted value is 30. If it is MSE loss, then the difference is 10, and then if you square it, it will become 100. But logarithmic loss is actually 0.07. Whereas if your true value is 4000 and this is 3000, 1000 difference is there. And if you take square of that, you see the MSE, how much it is coming, right? So, but your log value is still 0.082. So if the error is large, then there is a big difference here, but there is a small difference here. So the difference is very small here, 0.07 to 0.08. You see the difference here, right? So that is one thing with respect to logarithmic error. And we will see the disadvantages now. One thing is, as it is logarithmic, it is not directly interpretable. By seeing the error, if you want to say how good your model is, it is a bit difficult because it's not direct difference in the errors, right? It's not direct difference in actual and predicted. So it is a log application you are doing. So you are kind of adding non-linearity to your error function. So log is a non-linear function. So obviously when you have non-linear function, you cannot directly interpret how well your model is working, right? So that is why you can say that it is a little bit less interpretable. We have seen this, it is more sensitive to small errors, and similarly it is having a bit of bias to outliers. That means that whatever outlier is there, how much ever big it is, their contribution is becoming very less. So it is kind of saying that, okay, if you have a lot of outliers in your data also, it is okay, fine, leave them. So error is very less because of them. So it is kind of taking their side, right? So that way. And it penalizes underestimates more than overestimates. So what is this underestimate and overestimate? Underestimate is something when your predicted value is less than your actual value. Overestimate is something when your predicted value is greater than your actual value. So let's say your predicted value is less than actual value, that is underestimate. Okay, and overestimate is if your predicted value is greater than your actual value. This is overestimate. So we are saying that when you get this kind of difference, You are penalizing more when your prediction is less than actual, and you are penalizing less when your prediction is greater than actual. Let us see that. So if you see this here, right? This is my true value. Okay? This is my ground truth. 20 should be my ground truth. But if the prediction is 10, that means it is less than the true value, which is underestimate. If it is underestimate, then MSE will give 100, okay? And here it is overestimating. That means that it is giving more than the actual value, but still the difference is 10, so MSE will be 10 only. But if you check MSLE, logarithmic loss, your predicted value, you are taking logarithm of prediction, right? So you are taking log of 10 here, and you are taking log of 30 here, right? So for MSE it doesn't matter, both are 10, so you are squaring it, done. But your predicted value here is 10 and 30. So before taking the error difference, you are applying the logarithm. So here you are taking log of 10 and you are taking log of 30. So if you check this, log of 10 and log of 30, if you observe the graph of logarithm, the values around 10 or 15, the curve is not still flattened, right? So usually the value between 0 and 10, you can say that it is not fully flattened. So it is raising it, still the curve is still raising. So the curve is going like this, right? So let's say this is my 10, 0. So in between 0 and 10, the curve is still raising. It is not fully flattened out. But as it is going beyond 10, it is kind of getting flattened out. That is the reason if you take 10 or less than 10 for smaller values, which are underestimates, usually underestimates, your MSLE will be higher. Whereas if you have larger values, your MSLE will be less. Okay. So when you take the difference, I am saying, so you don't directly take like log of 10 is this, log of 30 is this. No. When you take the difference of log of 20 minus log of 10, that becomes this, and log of 30 minus log of 10, 20, that becomes this. Okay. So that's why, because of this difference, because of this curvature, the nature of this log curvature, underestimates, which are smaller values of log, okay, they will have more value proportion compared to overestimates, where you have larger values, which is kind of getting flattened out here. So that is the reason we say that it penalizes underestimates compared to overestimates. There is one more variant of mean square logarithmic error. You just take the root of it, just like you have mean squared error and root mean squared error, right? So MSE and RMSE. You take the root of MSE, it becomes RMSE. Similarly here, where you have the logarithmic error, you take the root of it, it will become root mean square logarithmic error. Whatever we are having till here, it is MSLE, and you take the square root here to make it root mean square. Why should we use square root? Usually root we have used in MSE for making it more interpretable. Because when you are squaring it, it is kind of, you are taking it into a different scale, right? Your errors get scaled up. But if you want to keep it at the normal scale, then you have to do the square root. That is what we did in RMSE also, from MSE to RMSE. Same thing here, you can apply the same logic here to understand why you should use square root, right? So it makes it more interpretable compared to MSLE. The same way, the calculation is the same. Till here it is only MSLE. So you do the same way. You take the logarithm, you take the difference of them, you take the square of them, and then you do that for all the samples, take the mean of them, and then finally you apply the square root. Okay, so this is root mean square logarithmic error. It is just a variant of MSLE. Okay, and now we will see the implementation. So this is the Python implementation. So for calculating the logarithm, we are actually using numpy function. Okay, numpy log, np log, wherever np log is there. So that means the logarithm function. Usually this is ln. Okay, natural log. So what we are doing here, whatever the actual value we are having, so this is y, we are adding 1 to it just to be safe side, because y can be 0. In that case, log of 0 is undefined. So that is the reason we add 1 here. The same way the predicted is y cap plus 1. You take the log of them. So log of actual, log of predicted you get. Then you take the difference of them. Okay. And then you take the square of them, square of the difference. And you take the mean of all the values. So once you take the mean, you will get MSLE. What about RMSLE? You need to take the square root of MSLE. That is what you will get here. So this is how you can actually implement. Simple, you can actually calculate the logarithm of the predicted value and the actual value before taking the difference. That is the only difference compared to MSE. So if you take mean squared error, instead of taking the difference, we take the log of the differences. Okay, log of the values and then difference. So that's the difference between MSE and MSLE. That is all about this loss function here. So we have seen why it is used. Main significance is when you have skewed data set, when your distribution is not following a proper normal distribution, which is kind of an assumption which we do when we are applying the regression task. So if your data is skewed data, then the regression will not work properly. To actually kind of suppress the effect of skewness, we use logarithmic error. That is one. And second thing is, main thing to deal with outliers. If you have outliers, then your error value is very high and your weight updates will be coarse. That means that large weight updates, weights will jump from one point to another point. It's not a finer value changes, right? In that case, what is the significance? Like it is kind of coming into the picture like your error value is very high. Your learning algorithm doesn't know whether it is contribution from single outlier or it is contribution from multiple normal predictions, right? We don't know that. So to reduce the effect of these outliers, we use logarithm. So when we have logarithm added to before taking the difference, your values will become smaller. So automatically the error will become small. So that is kind of balance the error between smaller values and large values, outliers. Hope you learn something from this. Thank you.